Hello and welcome to Build Your Own CPU Part 12. In this episode, we'll start looking at the motherboard and how it supports the CPU in its functions. Here we have a block diagram of the motherboard. In its heart is a microchip PIC microcontroller. This is here to simulate the RAM and the ROM. It generates the clock signals. It interfaces to the keyboard, the video display, and does the pages for the page memory. This all can be done in other hardware. Because this doesn't form part of the actual CPU, I decided to make this all out of ICs, and it was easier to do things in software because I can change like the memory map structure in software quite easy. The actual program for the noughts and crosses can be updated quite easily because I just need to update what's in the microcontroller. Now on the board we've got some LEDs at the top, and that's the address LEDs and data LEDs. They're just for show, so you can see that there's what's going on, what address you're at, etc. On the left there'll be a potentiometer for setting the clock speed, so you can speed things up and slow them down. There's also an auto manual switch, so you can switch the whole system to stepped control, where you can step it through a quarter of a clock cycle at a time. We'll go through that in more detail when we get to look at the software that's in the microcontroller in another episode. And then we've got a comms port on there, which isn't at the moment isn't used for anything, but could be. I'll just put it there because the facilities were available. And I did end up using the I/O on that to help me debug the system. Below that, we've got a demultiplexer for the clock cycles. So instead of using 16 separate outputs from the microcontroller, I just used 4 of them and demultiplexed them through to 74238s to give me the pulses out. So we got T15, which is a special case, which we'll go into later. The pulse output, which is actually a direct signal from the microcontroller, and T states 14 to 0, or 0 to 14, whichever way you count. Now there's also another group of LEDs, which are the control signals coming in and going out, so you can monitor what they're doing. Above that is the programming port, where you program the microcontroller. To the right of it, we've got a display, which is the 9 LEDs for the actual noughts and crosses. Below that is a connector for the keyboard, which feeds directly to the microcontroller. And just below that, there's a reset button, so you can reset the whole system if needed. So far, I haven't had to use that. On just to the right of that, we've got the data bus for data coming in and out, and the control signals, which, again, some come in, some go out. Here we have the circuit board for the motherboard, the one in black. So on the left here, we've got a green just general register. This is the memory address register. So output from here will be the actual address bus, which will jump across this card here. This is how they're laid out on the actual CPU. So these links come straight across and put the address into the motherboard. And on the other side, we've got the data bus, comes in here, or goes in and out there. And we've got the control bus here. Well, this will be the control bus. The control bus signals are here. They come across, will be linked to these pins, and they'll go across, and there'll be wire links that come down to here, which feed up to the control bus, which will be right up here somewhere. That's the control signals going in and out. Now, if we just look a bit closer at the motherboard itself, on the motherboard itself, we've got 2 ICs up here. These are just a row of LEDs for the address and data. I was going to do these with MOSFETs, but it would take up more board space than just doing it with these ICs. So you've got a couple of 74375s now. 573s? No, 573s. And they're normally latches, but they just pass straight through. These are the same ICs as what was used on the logic analyzer. I've got a bunch of them, so I used them here, and they're just used as drivers for the LEDs. Here is where the pot sits for the speed control. This here's a little jumper for the auto manual, again as shown on the block diagram. Here's the actual PIC processor sits in here, and that's the programming port. You know, it's these two little jumpers here, where you can jump across here, so that the pins coming in here are also used for the programmer. But when you're not using the programmer plugged in, when the thing's all active, you just want to link across. You've got D0 and D1 on your data bus. Display LEDs, tricolour LEDs, all serially addressable. And this is the keyboard connection. So you've got positive and negative supply, and then a voltage comes back, because whatever voltage it is defines what key's been pressed. And another one of these 74573s for these LEDs, which are the control signals. I also put the whether you're transmitting or receiving on there if you're using this bit here. That's your comms port that wasn't actually used for anything. Here are the two 74238s for demultiplexing 4 address lines that come off the PIC chip, and that's 16 possible outputs, which is your T states. So I'll just give 4 bits out of there, because I was running out of I/O on there, so I demultiplexed it. And we use 0 to 14. 15 goes off on its own. You've got an LED there for it, but I feed the reset signal through here. These signals here, they feed off the bottom and across to the demultiplexer board and the instruction decoder where they're used. And the pulse signal is used on a couple of the instruction decoders as well, so that was fed that way. And so the control signals here, we've got data output enable. That's basically your read signal. There's your pulse going out here as well. The pulse goes out in 2 places. This one goes to the instruction decoder. This pulse goes up the control line to the registers, etc. on the main CPU. It's the same signal, just fed out in 2 places. And we've got the I/O to say whether it's an I/O read or write rather than a memory. Then there's the reset signal, which comes out of here for a short while, but is normally fed back in to actually reset the processor there as well, if you assert that with the reset button here. But this reset goes out and resets all the registers. Then you've got the memory chip select, which is the opposite of the I/O. That's to let you know you're accessing memory. So you need both of those signals coming into here, so it knows what to emulate, whether to emulate memory or I/O, because the I/O is used for the video and the keyboard and the paged memory. And the bottom one is the read signal, to let you know whether it's a read. So that's your read, and that one's your write, basically. The read is coming in as well. And here's a circuit diagram on the dip trace. And if we zoom in, you can see it's just for the speed control, it's just a 5-volt supply across potentiometer to 0 volts, and we just pick off a voltage. And this uses an analog input on port A, and the value of that determines the speed that is clocking the processor at. Quite straightforwards. Auto manual, again, that's just a digital input, and if it's on a 1, it uses that value. If it's on a 0, then it's going to read the keyboard for you to press the function keys to tell it to step on. And we'll go through that in the software later. Now, just below that, we've got clocks 0, 1, 2, and 3. These are for the T states. So there's a possible 16 states there. And if we look at the 74238s, there's 2 of them here. So A0, 1, and 2 is wired the same on both of them, because these are 3 to 8 decoders. We've also got these enable signals. So the false signal, the top clock signal, on there it's not enable, and on here it's enable. So it's that chip or that chip. So the only problem here is, because you've got 16 coming in, so you've got 16 going out, one of them is always going to be on. And there are states where we want the T signals to not be on at all, be nothing there. As soon as T15 isn't used, I decided, well, that one, which gives you an LED there, well, if I switch all these signals on coming out, it will select T15, which doesn't actually go to the CPU. All it does is lights that LED. which, believe it or not, is more useful than you think. And the spare slot going out here for the T-states, I actually bought the pulse signal and sent that out of there because that is actually needed on the instruction decoder. So there's one group there, and there's the other group there. There's all your T-states. And again, that's just another IC for your lighting your LEDs. Now here's the control bus signals coming in, like the LEDs, or go across here to the actual inputs on port C of the microcontroller. There's the reset switch. Now you notice these two resistors here. When we start up, the microcontroller has this as an output, and it actually puts a signal on there going out to everything to reset stuff. But then it does that for 50 microseconds to reset everything, and then it turns it to an input. So then it's able to read the reset button, which also feeds out. But we have to have a resistor here so that the signal coming out here doesn't conflict with any possible signal coming out there when you first start up. Because when you do a reset, this is going to try and do a reset as well, and then you could have conflicting outputs on here, and it will damage the output of the microcontroller. So by putting a resistor there, I could have 0 here and 5 volts there, and that's 5 milliamps, which this can handle anyhow. So that stops you damaging the microcontroller. Now we've got an RC network just there to give us a nice smooth pulse. Now also on here, the spare outputs that I used for the transmit out and receive back in on a comms port if you wanted to add a comms port and thus control everything over a serial port. Now if we take a closer look at the programming port, you'll see here we've got RB0 and RB1 come out. They feed up to that port, and then you put a jumper across to feed them out and go out to the rest on the data bus to act as that. But when the program is plugged in, you can't do that. You need to have them disconnected. I was trying to debug the software on here, which I'll refer to as the BIOS. It's not really a BIOS, it's just the program that runs on that controller. But if you think upon it as being the BIOS of the motherboard, it sort of makes it easier to understand. So I needed to have the data outputs on at the same time. So I'll put links from these COM ports here across to here. And then whenever the program wanted to put B0, B1, that's D0 or D1 on the data bus, I put a patch in the program to put it out of these ports here, and then I wire them across there. So I could actually control the board while having the programmer plugged in and actually single stepping the microcontroller. That's not the same as a single step of the CPU, it's actual microcontroller single stepping, because there might be 100 instructions on the microcontroller for one step on the actual CPU. So this is the display, which is made out of serially addressable LEDs. So we've got one output here, it's pulsed output. It's one of the pins on the microcontroller. You just send a pulse stream out of here, data in, data out, data in. They're all serially linked up, and you send the data for this LED first of all. It'll come into this LED, and then when the next group of pulses come along, this will get transferred into there, and the new ones will go into there, and they'll gradually work their way along. And once you've got all 9 in, you stop sending data, and these then, after a short while, go, oh, that's the end of the data stream, and they do what you've just told them to do. So that's how you update your display, and you can do it all with just one data line. I've also fed that data line out of the keyboard connector, so that's the 5 volts to the keyboard and 0 volts, and your keyboard signal comes in here, keyboard in, but the display data can also go out there, so that if you wanted to have an external display, you could do. We can actually build it into the keyboard, so as you press a key, that key lights up. So you wouldn't need this on the motherboard at all, it'd all be in the keyboard. Now this is the circuit for the keyboard, all quite simple. All it is the 5 volts comes in here and goes down a load of 1K resistors. And when you press a key, it basically takes the voltage that's on this divider and sends it out back. So if you press this key here, you'd get about half voltage. If you press this one here, you'll be near the top. So each key has got its own voltage coming out. Now down here, the last resistor is a 4K to try and raise this voltage up a bit here to offset it, because you've just got your bog standard NPN transistor sending the data out, because you don't want to load up the signal coming through, because it will bias your voltage that you're reading. So by using an emitter follower, you decouple it, so the voltage comes in here. This will send the same voltage out there, minus 0.65 of a volt for the voltage drop between the base and the emitter. So let's just send the signal through here, and we tap it off and we read that voltage. Now this is a little bit supply sensitive. I could have built it a bit better, but it works well enough. If you know your supply coming in, which it says 5 volts, but on mine it's generally about 4.5, then your keyboard voltage is that if this supply varies, the voltage coming out your keyboard will vary slightly, because this is a fixed 0.65 of volts across there, but the voltage that's coming out of these points here will vary depending on your supply voltage. If your supply voltage goes down by 10%, the voltage on these will go down by 10%, but this voltage drop across here won't. So different supply voltages do affect it slightly. What I've done is I actually measured it and then calculated what values should be coming into the analog port on the microcontroller and adjusted it to match. This is the data sheet for the actual LEDs used. They're WS2812s, and you can have up to 16 million colours at 256 different brightnesses. I started off at full brightness, but I had to wind it down, it was too bright, and we'll see how that's done in the code. Quite simple, but it's got a specific way of transmitting the data. There's the actual specifications for the LEDs and how many volts the drops across them, etc. So here's the timings for sending the ones and zeros. When you look at the actual code here, if you want to send a 0, you have a short time here and a long time here. This is the pulsed output from the microcontroller. If you're sending a 1, then it's a bit longer. So this time here is critical, and this time here is critical. These ones, not so much, I found out. These can be anything up to 50 microseconds long. It doesn't say that in the data sheet, but they can be. It's these on pulses that are critical. And here you see you just daisy chain them all together. You can have as many as you like. I've done 120 of these in the past in a row. Works quite well. So the actual colours, you've got 8 bits for green, 8 bits for red, and 8 bits for blue. And you transmit them from this bit first. So if you want these 8 bits here, say how bright the green is going to be. So if you're going to send out, say a brightness of 127, you want G7 to be 0. So you'd send a 0. So you'd send this pulse here. So it'd be, sorry, this pulse here. So it'd be a short pulse on the positive, long pulse on the negative. So you try and keep all the pulse stream the same length. And then you'd go to this one, G6 after, which is BA1. So you would send that bit next. And then the next one will be a 1. So you just have a stream of these until you've got down to your reds. And then you send the red byte and then send the blue byte. Now that goes out and you think, well, that's the first one. Well, no, actually, that's the last of the LEDs you're talking to, because this data will get passed through from one out into the next. And it's not until you get the end pulse, which is this one here, which is 50 microseconds. Here we go. If we look at here, greater than 50 microseconds says you've finished sending all your data, and then whatever data is sitting in there gets locked in there. So I'm going to do 9 of these. So that's 9 LEDs with 3 bytes on each. That's 27 bytes in all. And we'll actually reserve 27 bytes of memory in a microcontroller, and we'll build up what the display should look like before we transmit it. And then I'll do one loop inside the other. The first loop will go through the bits, and the outside loop will be stepping between the bytes. We just have to put them in the right order. So here we go. It shows it here on the data sheet. That's the first group of 24 bits, which is your last LED. Then the next, second from last LED, then the third from last, and I'll be sending 9 groups of these. And then I'll stop transmitting for at least 50 microseconds, and it'll lock the display in. Here is the listing of the software for the microcontroller, and in here we do all the emulation of the ROM and the RAM and the region of the keyboard and center display and how we do the paged memory, etc. There's already enough in this video to be thinking about, so this one will take a little while when there's a bit more thinking involved. So I'll leave this to the next video, as in part 13, where you get to see all my dodgy software. So don't forget to like and subscribe. I hope to see you in episode 13.